In electrical engineering, we often encounter complex exponentials. And in this video, I'm going to try to give you some insight into what these complex exponentials are and try to visualize these complex exponentials. So a complex exponential is a function or a signal of the form e to the s times t. T is typically the time variable. So this is a function of time, and s is a complex number whose real part is sigma and imaginary part is omega. So visualizing these kinds of functions is usually a bit hard, and what you have to do is to visualize either the real part of this separately and the imaginary part of this separately, or the magnitude of this function and the phase of this function separately. So I'll try to walk you through both these approaches. And before we try to visualize these, let's take a specific example. So let's take an example where sigma is -1 and let's say omega is 2 pi. So then x of t is given by e to the -1 plus j times 2 pi times t. So what we're going to do first is to try to write this as the product of two exponentials. So I'm going to write this as e to the -t times e to the j 2 pi t. So notice that the second exponential has only the imaginary part in the exponent, and we have e to the -t, which is strictly real, have been factored out from this exponential here. So in the more general case, we would of course write it as e to the sigma times t times e to the j omega t. Right? But for this video, let's stick to this example first. Let's try to sketch the real part of this and the imaginary part of this. So what is the real part of this signal? So the real part of x of t is, notice that this is strictly real, and this e to the j 2 pi t can be written as cosine 2 pi t plus j times sine 2 pi t. Therefore, the real part is given by e to the -t cosine 2 pi t. So how does this function change with time? So notice that this function is a product of two functions. So let's sketch this function first, sketch this, and then we'll sketch the product so things become a little bit easier to understand. So the first function, so this is an exponentially decaying function, right? So this function is going to exponentially decay like this. So this takes the value 1 here. For negative values of time, this function blows up. For positive values of time, it decays. And then the second function we have here is a cosine function, and it's cosine 2 pi t. So this is a cosine, it goes like this. So this is 0, this is 1, so on and so forth. And the real part of x of t is the product of these two functions, right? So think about what's going to happen when we multiply this function with this function. So what's going to happen is we're going to get a function which looks like this. So we're going to have a function which crosses zeros exactly where the cosine was crossing zeros. However, the amplitude of this cosine is going to be multiplied by this exponential. So now you're going to get a damped cosinusoid like this. Does that make sense? And in the same way, we can plot the imaginary part, right? The imaginary part, it's going to, instead of a cosinusoid here, we're simply going to get a sinusoid, but the same, you're going to observe the same damping when you plot the imaginary part as well. So both the imaginary part and the real part are going to be damped sinusoids or cosinusoids. Just in the interest of completeness, I will go ahead and sketch the imaginary part. So this is clearly increasing in amplitude for negative values of t, and for positive values of t, it's getting damped out. Okay. Now, what I want to focus on here, so hopefully this example gives you some intuition, and now that we have this intuition, I want to go to the more general case. And what I want to really focus on is on the effect of this sigma and omega on this signal. So what's going to happen as we change sigma, and what's going to happen as we change omega? So what is going to happen as you change sigma is that as long as sigma is negative, this function is going to decay. But if sigma is large and is large in magnitude and negative, then this function is going to damp much quickly, right? The rate at which this function decreases is going to depend on sigma, as long as it's negative. If sigma is positive, this function is going to increase as t increases, all right? So whether this is a damped sinusoid or an increasing sinusoid depends on whether sigma is negative or positive. What about omega? Well, notice that omega is the frequency of this cosinusoid or this sinusoid. So if we increase omega, we're going to make increase the frequency of this cosinusoid or this sinusoid. So we're going to make the oscillations faster if you increase omega, or the oscillation slower if you decrease omega. But but omega is not going to affect the envelope of this curve. So this curve is going to have some envelope, and that envelope is e to the negative sigma t, right? That comes from this function here. Because this part of the exponential really does not, it has unit magnitude. The envelope comes only from this e to the negative t. But if you increase omega, then what's going to happen is this function is going to oscillate faster and faster. So for example, if you have a larger value of omega, we may see something like this. May see something oscillate faster like this. Okay. So now I'm going to try to plot the magnitude of x of t and the phase of x of t. So let's think about the magnitude of x of t. X of t is given by e to the negative t times e to the j 2 pi t. So the magnitude of x of t is the magnitude or the absolute value of e to the negative t, since e to the negative t is a real number, times the magnitude of e to the j 2 pi t. And notice that the magnitude of e to the j 2 pi t is always 1. Because if you think of this as a real number, it's 1 times e to the j theta. So the magnitude of this is indeed 1. So the magnitude of e to the magnitude of x of t is simply e to the negative t. So plotting the magnitude of x of t is pretty easy. It is just a decaying exponential like this. Of course, in the more general case, when s is equal to sigma plus j omega, then this function would be e to the negative sigma t. And clearly when, it would be e to the sigma t, not negative sigma t. I made a small mistake here. So s is sigma plus j omega, so this should have been e to the sigma t. And for our example, sigma is negative 1, so you can see that this is e to the negative t. So depending on whether sigma is positive or negative, again, if it's sigma is positive, it blows up. Sigma is negative, it damps down this way. What about the phase of x of t? Well, you can see from here, the phase or the angle of x of t. Now, this number is always real and positive, so it doesn't really change the phase of the complex number. And the phase of this is 2 pi t, because this complex number is of the form e to the j theta, where theta is 2 pi t, and so the phase function is just 2 pi t, so which means the phase function simply linearly increases up to pi, drops down to negative pi, so on and so forth. So the phase function looks like that. So this is t equal to 1, t equal to 1/2, 0, so on and so forth. Okay. Now, we will see these kinds of complex exponentials quite often in a couple of classes, at least in electrical engineering. And very often, you will need to understand the behavior of these complex exponentials as t tends to infinity or t tends to negative infinity. So typically, when you're trying to understand what happens to the behavior of some system in steady state. So if you wait for a very long time, what's going to happen to some system, you will end up needing to understand what happens to e raised to s times t when t is very large. So we'll just briefly talk about that. What happens to e to the st when t tends to infinity? So notice that e to the st is e to the sigma t times e to the j omega t. Now, if sigma is negative, then as t tends to infinity, this term is going to 0, right? This is exponentially decaying like this. Now, the second term is a term that is not well defined as t goes to infinity. So e to the j omega t is cosine omega t plus j times sine omega t. So cosine infinity is not a well defined term, neither is sine infinity. But that doesn't matter because this term is going to 0, and we know that this term never exceeds 1. The real part and the imaginary part, neither of them never exceed 1. So the product of these two is going to go to 0. If sigma is less than 0, then we can say that x of t goes to 0 as t goes to infinity. Whereas if sigma is greater than 0, then x of t becomes undefined. And when sigma is equal to 0 is still undefined because you just end up with this term. and this term becomes 1, and you are left with this term which is undefined as t goes to infinity. Oops, undefined. Actually, you can say if sigma is greater than 0, x of t becomes unbounded. Right, because this term increases, and so this becomes unbounded, and if sigma is equal to 0, x of t is undefined. It's not unbounded, but it oscillates as a cosinusoid or a sinusoid, but never reaches any steady state value as t becomes infinitely large. Now, of course, when t goes to negative infinity, we have the opposite of this. If sigma is less than 0 and t goes to negative infinity, then this signal blows up. Whereas if sigma is greater than 0, then that signal gets damped. And if sigma is equal to 0, it remains undefined.